AP 120, Chapter 10, Topics Vision. So we are now moving on to vision, which, as we know, is localized to the eye. So when we look at the eye, we also notice that there are important structures that assist our eyes. For instance, we have eyelids, upper and lower eyelids. They protect and prevent foreign objects from making contact with the eye, so provide protection. We've got eyelashes to try and catch particulates, materials that try to get into the eye. We have the conjunctiva, which is a thin membrane structure covering parts of the surface of the anterior eye and also lining the bottom, the inside of the eyelid that produce, well, mucus. So conjunctiva is good for mucus to moisten and lubricate the eye. The only place you do not find the conjunctiva is on the cornea itself. So the clear dome in the front of the eye does not have conjunctiva, only the whitish parts that you can see toward the front. Again, lubrication and reducing friction is the job of the mucus produced by the conjunctiva. All right, we also have lacrimal glands toward the lateral sides of the eyeballs. They produce tear fluid. Tear fluid is to lubricate and cleanse the eye. Lacrimal glands are constantly producing a tiny amount of tear fluid to keep the eyes moist. And it turns out that tear fluid will eventually drain through some tiny ducts to the nasal cavity. So tear fluid, lacrimal fluid, when it reaches the medial corner of the eye, is then transported down to the nasal cavity, which of course explains why we get runny noses when we cry real hard, because the nasal cavity gets flooded with tear fluid. Also, tears contain the antibacterial enzyme lysozyme, so it provides some antibacterial protection. There are 6 muscles that attach to the eyeball directly and are able to move the eyeball. These muscles are innervated by the oculomotor nerve, the trochlear nerve, or the abducens nerve. So the eye itself is composed of 3 layers. We have the outer layer or superficial layer that is composed primarily of the cornea, which is that anterior transparent dome that allows light to pass through, and of the sclera, which is the white opaque structure that composes the rest of the eye. And the sclera is made of dense connective tissue. It's very strong, and it helps to give the eye its shape, to provide some protection for the eyeball, and also is attachment sites for the muscles that move the eyeball. Then coming out of the posterior or back side of the eyeball is the optic nerve which carries the sensation of vision to the brain. And also blood vessels pass through that area as well. All right, the middle layer is a thin layer called the choroid coat. It also is made up of the ciliary body and the iris, but most of it is made up of the choroid coat. Choroid coat is darkly pigmented, so it's dark in color, and it's very vascular, has a lot of blood vessels. Blood vessels important for nourishing the tissues of the eye. And then that dark color of the choroid coat is important because it can absorb excess light that comes in the eye, so we don't have any feedback. The ciliary body is toward the front of the eye. It is a smooth muscle structure that's a ring shape going all the way around. And what the ciliary body does is it connects to the lens and is able, through muscular contractions, to change the shape of the lens, allowing us to focus the light that comes into the eyeball so we can see it clearly. So ciliary body, smooth muscle tissue forming a ring connecting to the lens. So here's the ciliary body. Here are the little fibers attaching it to the lens that are called suspensory ligaments. Holds the lens in place, changes its shape for focusing. And then we finally have the iris. The iris is a ring of smooth muscle tissue as well. It is in front of or anterior to the lens. And what the iris does is it adjusts the size of the pupil. And the pupil is a hole where light travels into the eyeball. So for dark conditions, the iris will dilate and allow a larger pupil and allowing more light to enter the eyeball. If we're in bright light, the iris will constrict, making the pupil smaller, less light gets in. And somewhere in the middle when we're at quote unquote normal light levels. So also worth noting is the iris is the part of the eye that has that color that when someone says you have brown eyes or blue eyes, that's what they're talking about, the color of the iris. All right, there is a space between the cornea and the iris and the lens, and that space is referred to as the anterior cavity, and it is filled with a fluid called the aqueous humor. All right, the third layer of the eye is the retina. So the retina is the innermost, the deepest layer of the eye. It is a thin, delicate tissue structure covering the back portions of the eye. It does not cover this area of the eye. And the retina houses the photoreceptors, houses the structures that detect light. Directly across from the pupil is a structure called the macula lutea. It's a little tiny depression, and at the center of the macula lutea is a region called the fovea centralis. Fovea centralis is where we have the absolute sharpest, best vision. So the macula lutea houses the fovea centralis, and this is where we get the absolute best, sharpest, clearest field of vision directly across from the pupil, where light's just going by a straight line. All right, when we look at the retina, we see that it is composed of a bunch of neurons leading to the sensory neurons that are carrying the signal out, and then also a series of photoreceptors. And these photoreceptors are the rods and the cones. So the two main categories of photoreceptors, rods and cones. The rods work best in dim light, and they do not detect colors. So everything they detect is in black and white. The cones work best in bright light, and they do detect color. I think it's red, blue, and yellow. And so the cones are what allow us to see the different colors that we can see. And they, of course, are connected to sensory neurons that then eventually lead to the neurons that send the signal out of the eye. So there is a thick layer of neurons. And what's weird is the pupil has the light come through it. The light travels to the back of the eye, where the retina is. It then has to pass through all these neurons before getting to the photoreceptors, which is a little weird. A consequence of that weird arrangement is that when the nerve fibers are leaving the eye and passing through what's referred to as the optic disc, because they have to push through where the photoreceptors would have been, there are no photoreceptors where the optic disc is located, which means we all have two little blind spots in our field of vision where there are no photoreceptors able to allow us to see in those spots. Those blind spots, however, aren't aware of them consciously because the brain fills in the blanks. So it just takes whatever is surrounding that little spot of nothing and fills it in. So the optic disc is the very beginning that leads to the optic nerve. And what's kind of cool is when optometrists look into your eye, they actually can see the optic disc and the macula lutea. The posterior chamber of the eyeball is filled with a gelatinous mass called the vitreous humor. The vitreous humor is important for supporting the retina, keeping it pushed to the surface of the inner eyeball, and it also helps to maintain the eye's shape. So vitreous humor is an important gelatinous mass. So again, light arrives. It passes through the cornea, through the anterior chamber, through the pupil, and then through the lens, and then from there it travels through the vitreous humor and hits the retina. So again, light travels first through the cornea, then the pupil, then the lens, then the vitreous humor, and then finally hits the retina where the photoreceptors are. Remember that order. All right, when light passes through the lens, the light rays are refracted. They are bent to try to bring the light down to a converging point. And that is what we need to be able to see things clearly. And it turns out the cornea and the lens, both of them are able to bend light. So the cornea has only one amount of bending that it can do, and it's static. The lens, however, is more dynamic and can change its shape to bend light, to refract light to different degrees. And normally light waves are focused on the retina, giving us a clear view of what we're looking at, although technically it's inverted. It's upside down image, but our brain compensates. So the rods, again, are more sensitive to light, so they work best in dim light. And there are chemicals in the rods called rhodopsin, and they are light sensitive, so that when light hits the rods, the chemical breaks down, and that generates the electric impulse. That is the signal, and then that signal gets passed on to the sensory neurons. So the chemical rhodopsin in the rods break down when exposed to light, and that causes an electric impulse, which gets passed on to the sensory neurons. Cones operate very similarly. However, they're able to detect color. Some cones detect red, some detect blue, some detect green. Looks like I was wrong earlier. Red, blue, and green are the three colors that are detected. If the cones are all active and detecting all three colors, then we get what looks like white. And if none of the cones are active, then we get the color black. And then when we have combinations of different degrees of activity for different colors of cones, then we get all the other beautiful colors we can see. Now, people with color blindness, they lack one or more of these proteins that detect these colors, causing them to be partially or completely colorblind. So we have the sensory neurons traveling from the retina. They pass through a structure called the optic chiasm, where half of the sensory neurons travel to the other side of the brain. From there, they go to the thalamus, and then from the thalamus to the visual cortex of the occipital lobes. So again, from the retina, we have sensory neurons traveling through the optic chiasm, where they might switch over, from there to the thalamus, and then there the signal gets further transmitted to the visual cortex of the occipital lobe. Anterior is normal vision, where the person who has 20/20 vision can see properly, can focus things to the retina. Hyperopia or farsightedness is when the light is too blurry because the eyeball is trying to focus too far away past the retina. So we don't get that convergence on the retina itself. And then, of course, we need convex lenses to correct that. And then myopia or nearsightedness is when it focuses too soon and things are blurry. So then we need concave lenses to correct for that so that the light focuses on the retina. All right, there are three main, most common three causes of blindness are cataracts, where the lens becomes opaque slowly over time, and what they see becomes fuzzier and fuzzier. Luckily, that can be treated by replacing the lens that's becoming opaque with an artificial lens. Then there's glaucoma. Glaucoma is when you have abnormally high blood pressure in the eyeball, and this can damage the neurons in the retina. It can cause blindness, usually starting with the periphery, so over time their field of vision narrows. And then age-related macular disease is a degenerative process breaking down the retina, and that starts at the macula lutea. And so when this happens, the person initially is losing their center of their field of vision, and then that can slowly expand over time to block all their vision. So three most common types of blindness. And that is it for Chapter 10.